Hello and welcome to this course, Advanced Robotics Applications. My name is Professor Ashish Datta. Now, this course is focused on experimentation and applications. But before we go on to applications and experimentation, I'll briefly revise about the theoretical aspects of robotics. For example, things like transformations, then forward kinematics, inverse kinematics, some amount of basics of linear control systems, sensors, actuators, microcontrollers. And once we are familiar with that, then we can see how we can apply this to robotic systems. That is, when you are saying you want to control a robotic system like a single serial arm or a mobile robot, how is the transformations that take place there? What is the kinematics there? And how do you actually control the system? Okay, so we'll first cover the theoretical aspects so that we can correlate that later and use it in the actual robotics experiments. Now, this is the first class, lecture number 1. So in this class, I'll basically discuss about the fundamentals of robotics, and I'll also explain to you how this course will be conducted, and then we'll proceed to the introduction and then consequently to more advanced topics. Okay, so this is Advanced Robotics Applications. Now, this course will consist of 8 weeks. So this is an 8 weeks course, and every week we are going to have 2 hours and 30 minutes class. So normally we'll be having 2-hour lectures, and then we may have experiments or we may have tutorials. And in some cases, we can have more number of lectures which are actually experimental demonstrations. Now, in total, we have 20 hours of lectures and tutorials, and we have assignments every week. So there is assignments every week which you're supposed to do by yourself. And at the end of the exam, at the end there will be an exam. So if you wish to take the exam, you can take the exam, and then you will get a certificate depending on whatever marks you have got. Now, you may have queries during the lecture hours because these are online recorded lectures. So you may have queries. So your queries will be answered by the TAs in the course. So we have 2 TAs who are senior PhD students. And also I will be there sometimes to answer your queries. So most of these queries will be answered online and via email. Okay, so this is the basic outline of the course. 8 weeks course, 20 hours lectures, and assignments every week, and then to be followed by a final exam at the end. Now, the course outline will cover these topics in this order. So first is introduction to robotics. That is, I will explain where robots came from. What do you mean by when we say that robotics is a part of automation? Then what do we mean by automation? What do we mean by robotics? Okay, and then we'll go on how robotics has progressed. So we had very simple robots which have progressed over the last couple of decades, and we have robots which are more or less autonomous, which can move around by themselves, can take decisions by themselves. Very often we use the word AI. So I'll also very briefly talk about what is this AI that we talk about in robotics. Now, after the introduction of robotics, we'll talk about joints. So robots, serial arms mainly, are made up of joints which are connected by links. And depending on the kind of joints and the link structures that they have, we can have serial arms, we can have parallel arms. Now, the area inside which a robot can move around is called a work volume. Okay, so it's called a work volume, and we'll see that different robots have different kind of work volumes. Now, a robot essentially moves around in space. So we need to know the relation of the end effector of the robot with respect to the base, if it's the case of a serial robot. But in the case of a mobile robot which is moving around, or an aerial unmanned vehicle which is flying around, you need to correlate the position and orientation of the end effector of the robot or of the mobile robot with respect to the world frame or the base frame, because of which you need to worry about various kind of transformations. That is, when the robot link is moving or the end effector is moving in space, how do you relate the position and orientation of the end effector with respect to the base frame? So what are the transformations involved? So we have basically 2 transformations. One is called the rotation transformation, and the other is called the linear transformation, that is the distance between the origins. So we'll look at these 2 transformations. How do you relate a frame which is rotating and translating in space with respect to the base frame? Now, when we are assigning access to a robot, we basically use the DH parameter notation. So what are DH parameters? How do you assign access to a robotic system? That we'll look at when we talk about DH parameters. Then with this basic, so these are basically the basics that are there. So these 3 are the basics that you need to know before you can just start the study of robotics. And after that, we have the forward kinematics and the inverse kinematics. Okay, that is, in the forward kinematics, if you are given the joint angles, what is the position and orientation of the end effector? Whereas in inverse kinematics, it is the reverse of that. If I give you the position orientation, what is the joint angles? Okay. Then we'll talk about sensors and actuators. Now, robotic link. Okay, if I talk about a serial robot like this. Okay, so most of the time we'll be talking about serial robots. Now, in the joint of a serial robot, these are actuated by motors. There is a motor, there is a gearbox in front, and there is an encoder or a position sensor sitting at the back. Okay, so this is the basic control structure of a robotic link, and every joint has one of these structures, one of these actuator sensor pairs. Now, how does the robot link move? You give voltage to the motor rotates, because of which there is an angular velocity at the joint, and because of the joints moving, the end effector moves, and there is a velocity at the end effector level. So what we'll need to see when we talk about control of a robot, or when we do experiments with a robot, we want to move this robot around in space. Okay, so we have to give corresponding voltage to the motor so that we can move it to the desired position, or we can impart a desired velocity to the end effector. Okay, so we'll look at sensors, actuators, then we'll talk about basics of linear control. So when we are going to give a voltage to the motor, how much voltage are you going to give? Okay, that would depend on what is the motion of the end effector that you require. Okay, so what ensures that? So basically we have to talk about linear control and how to design a controller for that. The controller is the one that is going to give the voltage such that it goes to a desired position. For example, if I want to move this and come here, okay, I want the robot link to move there. Then how much voltage should I give to the joint such that each of the joints will move by the desired angle, so that the end effector comes from here to here in some time. Now, what is the controller? So the controller can be a PC, or it can be a microcontroller, which actually ensures the control or enforces the control. So nowadays, because microcontrollers have become very, very cheap, and they are very easy to program, there are a lot of open source programs available for microcontrollers. It's very, very easy to make a very simple robotic system, either a serial arm or a mobile robot, and move it around. Hence, we'll be looking at microcontrollers. Now, in microcontrollers, how do you take sensor input output? So as I was saying, that at every joint there is a motor, there is an encoder or a position sensor which tells what is the position, what is the angle of the joint. Okay, so that is a position sensor which is marked here, and in the front there is a gear. So the microcontroller takes input from the sensor to find out what is the corresponding angle of the robot at present. Okay, and then depending on the desired position, it gives voltage to the motor. So that is essentially the task of the microcontroller. So it takes input output from the sensors, and it controls the servo motors or the motors which are actuating the joint. So this gives us the basics of control systems, sensors, actuators. After that, we move on to experiments. So in experiments, we have a couple of simple robots, which are lab-based robots which have been made. And we have a 2 degree of freedom planar arm, which has 2 revolute joints. Then we have a 5 bar 2 degree of freedom robot, again, which is also planar. Then we have mobile robotic systems, very simple systems which can move around, avoid obstacles, okay, follow a line. Then we have, after that, we'll come to a little bit more advanced applications like gait. So gait is the pattern of foot placement. So when you're looking at a quadruped robot, or you're looking at a biped robot, okay, then there's a particular sequence in which the robot moves. And that is basically what is called the gait of the robot. So how do you plan the gait of a bipedal system? How do you control a bipedal system for a gait? Okay. Then we'll look at industrial robots applications, mainly programming of industrial robots. We have robots like the Puma robot, one of the earliest robots, and Swaya robot. So this is also a cobot. You might have heard the word collaborative robot or cobot. So Swaya robot is a cobot in the sense that it can collaborate with a human. What do I mean by that? In the case of a Puma robot, you can write a program in Val2. Okay, we'll come to Val2 as we go along. It's a robot programming language. But you cannot catch the robot and move it around, I mean physically. Whereas in the case of the Swaya robot, which is a cobot, you can catch the end effector and move the robot around. And whatever motion you're doing, it will follow the motion. Okay, it will record the motion and follow it back. That is basically what we mean by a collaborative robot. So these are the topics that we'll be covering in about 8 weeks. Now, let's move on to the first topic. That is what I just talked about, is the introduction to robotics. That is, where did robots come from? Where are we at present? And what is the direction in which robotics is progressing? And what do you expect a robot to be in the future? Okay, we'll briefly also discuss about things like AI. What do you mean by AI? Because there's a lot of talk of AI these days. Okay, so the first thing that we'll look at is where robots came from, where is robotics technology at present, and where are we going in the future. So it's interesting to note that this word robot, almost everybody would have heard about the word robot. And if you ask somebody that, what do you think a robot is, you'll get some answer. And that actually shows the level to which robotics has permeated into society today. Okay, that right from children to people in cities to villages, and also in different countries, everybody thinks of a robot having particular attributes. Okay, so if somebody were to ask you that what do you think a robot is, or what is a robot, okay, different people will get different answers. For example, some people think that they are mechanical machines. So this is probably one of the most common. They are mechanical machines to do dirty jobs in industries. Some people might say that they are companions and friends. Okay, in many advanced countries, robots are living in homes of people. Okay, so they are companions, they are friends. If you ask children or kids, they might say robots are pets and toys. So today there are a lot of toys in the supermarkets which are called or named as robotic toys. You might have seen them around. Okay, so kids might say the robots are toys actually. Then they may be helpers. Okay, helping people in not only in industry, for example, in a railway station or in airport, they could be giving directions. Okay, you might have seen them around in several places. And lastly, but not the least, we have a lot of movies. There is a lot of coverage on television. Robots are also dangerous machines. For example, robots are also used in defense applications. Okay, in wartime applications, for example, drones, which are unmanned aerial vehicles. That's also a robot. Now, robots are also used in various kind of demining applications, explosive hunting applications. So robots can also be called dangerous machines. So depending on whatever your age is, what your background is, which country you're from, and how much TV you watch and how much of movies you watch, you will talk about a robot in some of this. You'll talk about a robot having some of these attributes. Okay, so it's very interesting that you'll rarely find anybody who has never heard about a robot. Okay, now so robotics started off as an offshoot of industrial automation, which is very, very old actually, as we'll see as we come along. So robotics essentially started off somewhere in 1960s in the industries for industrial applications like spot welding and spray painting. So this is probably the past. When we say the past, about 1960s. Fast, and they're much faster. Now that is the past. Okay, it's also there now. It's not like it's not there now, but this is where robotics started off. Industrial applications, it started off. Then if you look at the present, the best example would be the Amazon warehousing
collection of thousands of pods containing tens of thousands of inventory items, and a collection of pack workers on the side of the building, as you saw. And the whole process begins when Mrs. Smith goes to the website and orders red, green, and blue. And she says, submit order. Now our job becomes to find the pod with the red T-shirt that we want to use, match it up with the station, match it up with the robot, and then we hand out a mission to the robot. So we choose a bot and say, you're the guy, and we send it on a mission to go and fetch that pod. And we ask it to drive in Manhattan-type north, south, east, west trajectories and to tunnel underneath the other pods as much as possible, leaving the highways clear for inventory traffic. When it finally gets to its destination, it actually does a corkscrew motion to lift the pod just a little bit off the ground so we can carry it, and then it'll actually step out onto the local street, and from here it's trying to make its way up to the front of the building where that highway is. So highway driving is really the process of getting on the highway, moving down to the queue, the target queue, and then moving into that queuing system. And there again, what we're trying to do is just make the work, so it's actually a lot easier when they move in real time to get across the highway. But you can see them drifting across the highway there. And we're just trying to arrive in the queue in time for the next pick. We don't want too many there, we don't want too few there. Here's an overhead view of the queuing that takes place or takes over at this point. Supporting the pick worker, they reach in, pick, scan, pack, collection of thousands.
Now, if you look at the future, okay, now the future is what we call social robotics, collaborative robotics, cobotics. Now, when we use the word robot, I don't essentially mean that it has to be a piece of hardware. It can also be software. It can be a chatbot, okay, something like an online gaming or an online assistant. Okay, so Alexa in a way is a robot. Now, in terms of the future, social robots are expected to be the future, and they're already there. For example, things like clones. So here, this is a person who has made a copy of himself. Okay, now you can't make out which is the robot and which is the person. Then we have a teacher. So this is a teacher, and such robotic teachers are already there in many countries. Okay, many countries like the Scandinavian countries, they have shortage of elementary school teachers, and they are employing robotic teachers there. Then we have things like, so this is also an example of a robotic helper or a robotic assistant who can give answers to very simple questions. For example, in a railway station or in an airport or in a museum, if you want to know how do you go to some point, you can ask and the robot can answer and tell you. Sometimes the robot can also guide you and actually take you there, that this is how you go there. So this is the future of robotics. Now, what we see is that robotics essentially came from or started off with industrial automation. That is, robotics started off here with industrial automation, car manufacturing. Then it came to
collection of thousands of pods containing.
Then we have the future of robotics like social robots, collaborative robots like cobots, okay, and chatbots. So these are all different kinds of robots which are there today. Now, if we really look at the topic of automation, we see that robotics is a small part of automation. Okay, and automation, what is the definition of automation? Automation is essentially replacing human muscular power. Okay, so if you're performing a task where you're replacing human muscular power in some automated way, then you can call it automation. For example, you can have home automation, you can have office automation. Okay. So it's all, the whole idea is that whenever you're replacing human muscular power, we can call the process automation. Now, this business of automation has been going on for thousands of years. It's not like somebody invented automation one fine day. Okay. So people have been making tools, and tools make better tools. So right from 10,000 BC, that's very, very long time ago, human beings started using stone tools, then they started using iron tools, then copper tools, in that order. And today we know that tools make better tools. Okay, so for example, you have an NC machine. From an NC, you have a CNC, then you have an FMS, you have a SIM, in that order. Okay, so tools make better tools, and this process has been going on. So this process of automation has been going on for a very long time. There have been an example of very simple automation right from 150 BC. For example, the moving engine, Heron's door in Greece. This is an example of the first steam engine. Now, if you look at the date, it's about 150 BC. So that's very, very long time ago. How this works is that they would burn fire under this container, which contains water, and steam would be produced. Now, in this hemisphere, you can see steam will come out from these two directions. Okay, and there is, about this axis, there will be a moment generated. So if there is a force here and a force there, which are in opposite directions, so it will tend to rotate about this axis. Now, this is probably the first example of the steam engine. Okay, then this is an example of Heron's door. Again, why are we saying this is automation? Because there is no human being involved. Okay, you can see. So how does it work? How does the door open and close without a human? They would burn fire there. This will increase the temperature. This will increase the temperature of the air inside there and increase the pressure of the air. So what will happen? It will come down this way and press this liquid, which is water. So what will happen is, because the pressure there increases, it will force the water into this bucket. And once the water level here increases, the force downward, mg, will increase. So when the force increases, what will happen? This will tend to rotate in that direction. If it rotates, the door will open. Now when the fire is put off there, so the fire is put off, what will happen? The pressure will decrease. The water will flow back into this one now. The weight will decrease onto this bucket and the door will close again. So this is the simple example of automation, opening, closing of door, rotating a steam engine just without any muscular power, by using pressure, by using steam. And that is essentially where automation started off. Now, as we progress, so we see that 10,000 BC, then we have about 150 BC. Then about 1780 saw the creation of automatic dolls, which could draw and write pictures. Even today, these are there in various museums around the world. Small dolls which operate based on this spring base. So there is a key. If you wind the key, the spring gets wound. And using that energy, the dolls can do very simple things. Then we have punch cards. Now, then as we progress further, we see about 1801, this gentleman called James Chirag. Okay, he is the one who invented this programmed textile looms or programmed power looms. So even today, when we make textiles, basically it is made in this loom, and very often this is manually operated. You must have seen this textile looms. Either you have seen the physical machine or you must have seen it on TV or in movies. It's used even today. So how this operates is that there is this thread which moves around. So when they make these textiles or cloth, there are these layers of thread which are there. And if you want to make a pattern in that, what happens is that suppose this is a white base threads which are there. If you want to make patterns on this white thread, what the weaver who is sitting here would do is he will take a colored thread and then pass it in different directions. Okay, and that is how the designs are made on the fabric. And how is that done? So there is a lever which is pulled and which changes the position of this thread in between these threads. Okay, and that is how the fabric design is made on fabrics. Now, what this gentleman James Chirag did is that this program or this pattern he embedded in a program in a punch card. So this is a punch card, and he embedded this design in the punch card. Okay. Now the punch card is very similar to the OMR sheets that you use today for your exams. So in the OMR sheets there are holes like that. Okay. And what we do these days is we just color it, we darken it with a pencil, or we leave it blank. So it's a 1 or a 0. Okay. Now in the earlier punch cards there used to be a hole or no hole. Today we have it's either left blank or we color it or we darken it using a pencil. The meaning is the same. So this was the first application of punch cards. So the earlier computers programs were also made were run using punch cards. NC machines were run using punch cards. So whatever program was written was embedded in this punch card. Today we don't use punch card anymore. After punch card we had magnetic tapes, and then we had direct, where you can enter the program onto the memory of the system and you can run it. Okay, but just to see in terms of progress of automation, from very simple 10,000 BC, 150 BC, then we came to 1780 and then 1801, where different kinds of automation has been built and automation has been progressing. Of course, there are no robots till now. This is just talking about automation. Now, as we go further, what we see is that in 1904, in the Ford Motor Company in Detroit, so it was Henry Ford who first developed the concept of the transfer line. And transfer lines are used for assembling cars across the world today. Anywhere in the world, in India or any part of the world, you see. So what is a transfer line? So you must have seen these transfer lines. Either you have seen it in companies or you have seen it in movies or on TV. So this is a conveyor on which the car body is kept. So that's the car body which is kept. Okay. And this car body travels. So the conveyor moves and the car body travels to different locations. So it goes to different stations and it stops there. Say, for example, the car body stops here. And there would be a person who would do something on the car body. For example, the person can mount the wheels of the car body. Then after the wheels are mounted, it goes to the next station. Okay, maybe it's here. So in the next station, what happens? The person maybe mounts the door. Okay, so this way, the person is fully assembled in a transfer line. So a transfer line is a line or a conveyor in which the car moves from one station to another station. At each station, something is done by a human or by a robot, and then finally it comes out from the assembly side. Okay. Now this was invented by Ford Motor Company by Henry Ford, and it is used even today. Okay. This again is mechanical automation there is no robot as of today, as of 1904. So just for historical sake, where did the word robot come from? So 1921, okay, the Czechoslovakian playwright or a drama writer, Karl Čapek, he first used the word robot. So the word robot actually comes from the Czechoslovakian language, which means mechanical men. So in this 1921, Karl Čapek wrote a play, which is supposed to be here, shown here, that in future there will be mechanical men who will be replacing human beings to do dirty work in industries. Of course, there was no robot as of that day. Okay, but the word robot, just for historical interest, came from his play, 1921. Then 1942, Isaac Asimov first used the word robotics. So Isaac Asimov, you might be knowing, is a science fiction writer, and he's written a lot of books about the future of robotics, and a lot of his books have been made into movies today, like iRobot. Then he also framed the 3 laws of robotics. Now, he's the one who first used the word robotics and said in future there'll be a subject called robotics, and this is what it would contain. And actually, his books talk about robotics in the next 200 or 300 years. Okay, that is interesting, because there was no robot at that time, and yet he could imagine that in future there will be robot and there will be robotics, and this is what they would do and this is what they look like. Okay, that's very, very amazing. Now, as of 1942, of course, there is no robot till then. Okay, so where did the robot come from, or who is the father of the robot? So the robot essentially was developed in 1945 during the Second World War. So during the Second World War, they were developing the atom bomb, or in the atom bomb project, they were using material like uranium-235 or plutonium, okay, for making the atom bomb. And because this material are radioactive, they could not go near this material. So they had to handle it. So to handle this radioactive material, they made a device which is shown here, which is called the master-slave manipulator. So it consists of the master on one side and the slave on the other side. And there is very heavy shielding between them. So there is a wall which can be a few meters thick. Okay, and there is a window through here through which there is a liquid filled or oil filled. So you can see through, but the radiation from this side cannot go through. Okay. And how does it work? Every joint here is connected with a wire rope through the pulley. So there'll be a pulley here, it'll go on this side, there's a pulley there, and it'll go to the corresponding joint there. Okay. So the master will stand here and catch this device. Okay, so the master stands there, holds this device. Now if the master pulls it on this side, what will happen? The tension on the wire here will change. So the tension will go through, the tension here will change. So this, if he pulls it this side, then what will happen? This will move this side because of the change in tension. So the master could move these joints around, and each joint is connected to a corresponding joint on the other side with a wire rope and pulley. So you could move this around. This has a gripper there. So you could move this around, do very simple tasks like catch an object, put it somewhere, maybe pick up an object from here and put it here. Okay, that you could do. Very simple things. Okay, pour some liquid, you could do that. Okay. But here again, some things to note. This is strictly a mechanical device. Okay, there is no electronics here. There is no sensors, actuators, nothing is there. It's just a mechanical device, and motion is transferred by wire ropes and pulleys. Okay, so this is a mechanical device, and it's called a master-slave manipulator. It is also called the father of the robot. Now, so after this, what happened is, or rather what changed everything, what I mean is mechanical systems became electromechanical. So till here you're seeing that there is no concept of reprogram, there is no controller here. Okay, so invention of what changed everything. Okay? And this sometimes we call as the first revolution. Okay. Now what changed everything is the invention of the transistor, 1948-49. Now with the transistor came the microprocessor, and then came the computer in that order. Then we had the microcontroller, DSP, FPGA in that order. Okay. But all this started off with the invention of the transistor, 1949-48. And with the microprocessor came the concept of reprogram. So now you have a controller. Okay. And this controller, by changing the program in the controller, you could make a mechanical system do something different. Okay. So till now what we are seeing, what I mean is till here, 1945, there was no way by which you could embed a program and make it do something different. Okay. Because there was no concept of program till then, because there was no microcontroller or no computer. But with the transistor came the computer and came the concept of reprogram. So you could change the program, make the device do something else. So in 1950s, we had the first robot, which is shown here, which is called Shaky. So this robot is called the first mobile robot. It's a very simple robot which could move around, avoid obstacles, and it is called Shaky. It was developed at Stanford University. And 1952, which we have George Dowell, who made the teach and playback devices for NC machines. So NC machine, as you would be knowing, is called numerical control machines, or control by numbers. Now, an NC machine and a robot are fundamentally the same. So in terms of control structure, as we'll go on to our experiments, we'll see that when you're controlling a robot, you're controlling using numbers. Say, for example, if there is a serial arm here, okay, this is just an example of a serial arm. So if the arm is here, you want it to go there. What will you do is you will change the angles. So theta 1, theta 2, theta 3. Suppose it is at this angle, you'll give it a different angle there. So this is maybe 20 degrees. You want it to go to 70 degrees. So these are numbers, 20, 70 are numbers. So we control this robot using numbers. That I am at 20 degrees, I want to go to 70 degrees. Okay. So correspondingly, the controller is going to give a voltage and actuate the motor and take the link from there to there. So this is how a robot is controlled, by the input of numbers, and hence a numerical control machine and a robot are fundamentally the same in terms of the control structure. So from 1950 to about 2000, and today about 2024, this has come a very, very long way. Okay, so 1950 we had a very simple robot which was moving around doing something, okay, avoiding obstacles. But today we have a robot which is we have robots like this, biped robots, which are intelligent in a way that they have computer vision, they have force torque sensors, they can sense the environment, they have speech recognition. Okay, they can sometimes decide and take autonomous decisions. So in just 50 years, going from here to here is a big leap. Okay, and what we need to keep in mind, or what I'm trying to explain in this class, is that the first thing that happened was the creation of the robot, or the development of the robot, that came through because of the invention of the transistor. Okay, that is the first revolution. Now, to come from here to here, we have two more revolutions, and that is what I'll discuss about today. So first revolution, transistor. Now, with the invention of the transistor, we had a computer, or a microprocessor, which was running a computer, and we had a program which was run on a computer or a microprocessor, and which controlled one machine, like an NC machine or a robot. So this could have been an NC machine, or it could be a robot. Control structure is the same. Okay. Now, if you look at as time progressed, the computer became smaller and faster. We had faster and faster processors, and the machine became smaller and the machine became faster, because of which we had one computer controlling one machine. But then as the machine became faster and more powerful, we had one computer controlling many machines. Okay, so from NC, we ended up having CNC, computer numerical control, essentially because the computer became faster, so it could control more machines at the same time. So we have NC, we have CNC. Now, if you look at in terms of historically how this happened, it essentially happened because the machine became smaller and faster. Then we have NC, CNC, DNC, FMS, flexible manufacturing systems, where a computer, a PC or a computer could control many different kinds of machines together. For example, a parts carousel, machine tool here, machine work table, a robot, an ASRS. Okay, so the computer is becoming more and more powerful, and it is able to control many more machines at the same time. Then we have computer integrated manufacturing. Now, integrated manufacturing means the computer has become so powerful that it can control different aspects of manufacturing. Okay, so not only it is controlling in this particular case, it is controlling the movement of the vehicles on the transfer line. It can also control the robots. It can also control material scheduling. Okay, so it can actually integrate manufacturing, and it is almost like it is taking over the manufacturing and can control the full manufacturing process. This is called computer integrated manufacturing. And this essentially happened because the computer has become more and more powerful. So we see NC, CNC, DNC, FMS, SIM, in that order. So while we are at it, we can just talk about Industry 4.0. So these are some terms that you might hear or you might have heard. So what is Industry 4.0? So some of the industrial when we talk about industries, they are divided into first generation, second generation, third generation, fourth generation, also called industry 1.0, 2.0, 3.0, 4.0. What is the difference between them? Essentially, the power, where the industry is getting its power to do the job. What I mean, either power or energy. Okay, let's call it energy. So in this industry 1.0, all these industries used water power or steam power for performing their tasks. For example, in the earlier days, they would have used steam power to move something, okay, or water power. They are all industries which are in industry 1.0, and this is before, say, about 1700, about 1800. So before 1800, most of the industries that were operating, they used the kind of energy or power which was water power or steam power. Then we have what we call industrial revolution in England, and that is where electricity was the basic power. So machines which were run using electricity. Okay, so this is about after 1800s. Okay, and this is our industrial revolution that we talk about. So we have mass production, transfer lines, that came about because we were using electricity basically as a prime mover. Now the third generation, so this is 2.0, the third is 3.0, and in 3.0 is basically computers and automation. In India we call it the IT revolution. This is about 1970s. Okay, so it's basically computers and automation. So the computer is taking over or controlling all of automation, and that is basically what we call in India as the IT age. Okay, now after this we have about 2004, which is 4.0. Now the difference between 3.0 and 4.0 is that we have computers and automation here, but here we have computers, automation, and humans together. And this 4.0 is sometimes called cyber-physical systems. So it basically means that you have machines, you have computers, but you also have humans in the loop and some kind of AI or virtual reality. Okay. There are many examples of 4.0 today. For example, your Ola cabs or Uber cabs, when you're operating or when you're looking for a taxi, okay, you look for the taxi on your mobile phone. So from the mobile phone, it goes to the virtual world, where there would be some scheduling or some algorithm which is going to decide which taxi will come to you. Okay, and hence you have a connection involving machines, humans, and AI. And this is basically what is called cyber-physical systems. So the essential difference between 3.0 and 4.0 is that in 4.0 we have computers, we have automation, but we have also humans in the loop, and we have either virtual reality or intelligent systems or intelligent algorithms in the loop. Okay. Now, what is the definition of a robot? Well, nobody seems to agree. Okay, that's the interesting part, because different people would say the robot is different things that we have seen today, that if you ask somebody about a robot, they'll all give you different answers. But although nobody seems to agree, but to be called a robot, we understand that a system should do some or all of the following three things. Okay, so for a system to be called a robot, it should do some or all of the three things. What are the three things? One is move around. It should move around. Now a robot essentially moves around, and this we know because serial robot arm moves around. Okay, a mobile robot of course moves around. So a robot essentially moves around. Then it should sense and manipulate the environment. It should sense the environment. So the robot, a mobile robot moving around, should be able to sense that if there's an obstacle and avoid the obstacle. Okay. Serial robot arm should be able to manipulate the environment, pick up something, put it somewhere. Okay. For that, it needs some kind of sensors. And it should display some kind of intelligent behavior. Okay. Now, the third one, intelligent behavior, is not that easy to explain, because when we say intelligent, what do we mean? How do you know if a machine is intelligent? Okay. So this is a little tricky. Okay. But we understand that if it has some kind of intelligence, it can be classified as a robot. So to be called a robot, a system should do some or all of the following. So if it moves around, it's fine. If it senses and manipulates the environment, it's fine. Or if it can display some kind of intelligent behavior, then also we can call it a robot. Now, by this three, is a CNC machine a robot? Well, if you just think about it a little bit, we know that a CNC machine does not move around. It does not sense and manipulate the environment, and it does not display intelligent behavior. And hence, a CNC machine is a machine tool. It's not a robot. Okay, a CNC machine, you may argue that the cutting tool is moving. Yes, but the cutting tool is just moving as per the program. If you ask it to move X, it will move simply X. So there is no way it senses the environment and it manipulates the environment. It doesn't do that. Okay. So a CNC machine is a machine tool, it's not a robot. Now, consequently, after the first development of the robot, 1960s, we have had 4 generations of robots. So the first generation of robots, 1960s, it could simply pick and place devices with no external sensors. So these are the earliest robots that were made in industrial applications. Second generation, they have more interaction with the environment. For example, they have external sensors like computer vision, they have force torque sensors, and they can interact with the environment. Okay, so these are second generation robots. Third generation robots are the ones that are intelligent. They are autonomous in some way. For example, an unmanned aerial vehicle has some amount of intelligence. We can argue on that. Then, so this is the third classification of robots. So if I say this is 1960s, this is about 1980s, and this is about 2000. Okay, in the year 2000. And this is the future. So future is 2020 beyond. Okay, so we have robots which are biorobots, are there, micro, nano, and cyborgs, androids, and whatnot. So these are the basic definition. These are the basic divisions of how many generations of robots are there. And we can see that there are essentially 4 generations of robots. And the basic fundamental difference is how much they interact with the environment and the level of intelligence. Okay, that's what defines the 4 generations. Now, the first generation we have looked at is the transistor, 1948. Now, 1970, we had VLSI, which is very large scale integrated circuits. Okay. Now, the computers which was made about 1960s was very, very large in size, and they consumed a lot of power. They were made using this diodes and triodes and vacuum tubes and whatnot. So they were big, they were very expensive, and they consumed a lot of power. So they could not be used very easily. Now with VLSI came where you could have all this electronic components made onto a board, onto a motherboard. So you have one motherboard on which all the various components are made in the form. The old triodes were all converted into into various kinds of chips. And with this very large scale integrated circuit, what we have is we have a motherboard with various components put into that, like the way we have today. If you have looked at the motherboard of the PC or the laptop, or if you look at your mobile phone, it's just one board. The various components are stuck onto that, and that has happened because electronics has become smaller, faster, and cheaper, essentially because of VLSI, this very large scale integrated circuits. So you could make very, very large scale circuits, integrate them make them on one motherboard. And that is basically the VLSI technology, which came about 1970s. And because of this, electronics became smaller, faster, and cheaper. And today we have electronics which is very cheap, which is very fast, and very, very small. For example, the example is your mobile phone. We can talk of simpler examples like the computer mouse that you use, webcams. Okay, this all happened because of VLSI. Okay, cameras were there. Cameras were always there. CMOS-based cameras were there, but they were very big, but they were very expensive. But with VLSI, you could make electronic circuits which are very small, very cheap, and very fast. And because of which we have seen this sudden increase in the use of electronics everywhere. Okay, not only in industries, home applications, personal applications. Today, you rarely find any application or a device which does not have some sensor or some actuator in it. So this is also called the second revolution, 1970, invention of VLSI. And with VLSI, we had different areas, essentially because the computer became faster, smaller, cheaper. People could use the computer, it became cheaper. We had new areas like computer vision, advanced sensors like gyros, inclination sensors, force torque slip sensors, advanced controllers like microcontrollers, DSP, speech recognition, AI, all came about 1970s, essentially because of this concept of VLSI, because of the invention of VLSI. So this is our second industrial revolution, in a way. Okay, so the first one is the invention of the transistor. Second is the invention of VLSI. Now, if you see further, 1990s, we had new materials which are called smart materials, by which we could make smart actuators, smart sensors, and there was an interest in emulating biological designs, either in terms of control, in terms of design, okay, or in terms of learning-based systems. So this concept of or interest in emulating biological designs came about in this time, okay, and that essentially happened because of this invention of smart actuators, smart sensors. Now, just to give you an example, we had DC motors to make robots, either serial arms or mobile robots, but these DC motors, you could not make them very small. Well, how small? If you want to make nano robots or micro robots, which are very, very small, less than a millimeter, okay, you could not use a DC motor. Why? Because if you make a very small DC motor, it cannot give you that kind of power or that kind of torque. Okay, so you could not essentially make a conventional actuator small and still make a smaller robot out of it. So if you cannot make a DC motor small, you have to find some other actuator, and those actuators are basically called smart materials based actuators, and those are called smart actuators, smart sensors. The smart actuators, sensors, they can move systems, but they don't operate like DC motors. I'll just explain as we go along. Okay, and that gives rise to new areas like nanorobotics, microrobotics, etc. Okay, so the third generation is here: smart actuators, smart sensors. Now, the future, there are so many applications which are there as of today. We have biorobotics, emulating biology, nanorobotics, microrobotics, exoskeletons, wearable robotics, wearable devices. So there are robots which you can wear. They can help us to walk, to perform tasks. Neurorobotics, cyborgs, androids, robotic drugs, robots that can go inside the body and perform a particular task. Assistive robotics, rehabilitation robotics, outer space and nuclear robotics applications were always there. Okay, defense, this is an area which has become very, very important now. Okay, in terms of autonomous armaments, autonomous weapon systems. Okay, replacement of body functions, artificial muscles, Internet of Things, cyber physical systems. This is another area where we are in now. Okay, and the future, God only knows what more is going to come up. Okay, so if you look at the future, the direction is in terms of having robots having different kind of actuation and sensory devices and having more amount of intelligence or decision making capability. Okay, I will not use the word AI, but let us say more advanced decision making capabilities. These are some examples of where are we. This is 2016, so we are already there. Okay, this is actually almost 10 years ago. So micro robots, micro means how small. So they are so small that they can be injected into the bloodstream. So this is your bloodstream. These are the red blood cells. So the robot can go inside the bloodstream and perform particular tasks. Say, for example, if there is a tissue or a cell which has to be killed, okay, then it can go and target this cell and give targeted drugs. So we are at the scale where it can go inside the blood vessel. Okay, this you already know, because I'm sure that when they implant the stents on the heart, okay, they insert it from the thigh muscle, from the thigh vein, or from the vein in your arm, and they can take it to the point where they want to put the stent, and they can put the stent there and come out. Okay, so we are already at that scale. Bypass surgery. So robots can be made to go inside or can be inserted into the body. They can go in somewhere and do some task like give or deliver drugs at a particular location and come out. Okay, and even do surgery and come out. For example, here there is a bypass surgery. So there is a block on the artery. So to remove this block, there is a small robot which has gone in. It can drill the holes and remove the block and then come out. Okay, or if there is a cancerous tissue which needs to be killed, okay, so it can go and deliver drugs in that location and selectively target that area only. So we are already at that scale. Small robots which can act as micro dentists. They can go and clean your teeth and come. Some of these are very, I don't know, it sounds like science fiction, but it's already there. Robotic haircut, again, this system of haircut is there in many countries around the world. Then I talked about artificial muscle. So this is an artificial muscle or a smart actuator, artificial muscle or smart actuator. Now this is a robotic hand which does not have linkages and motors like a conventional robot, right? But yet it can close and open. Now how does it do that? Is these materials are what we call as made up of smart actuators. So this is a smart actuator, and it is an electroactive polymer. So it's a polymer. So it's a polymer like this, and on both sides of this there is a plating. There's a gold plating, okay, which you can see the golden color there. And if you give it a voltage, so if I give it a voltage there, Okay, so if I give it a very small voltage like 5 volts, it bends in one direction. So this will bend like this. This is what it is doing. So how is this hand actuated? By simply giving it a voltage and reversing the voltage. Okay, now there is no motor or anything actually there. So basically what we can see is that in this smart actuators, okay, you can they behave like actuators but are not DC motors. Okay. Actuator basically means they can convert electrical energy to mechanical motion. Okay, that's an actuator. So you can see that this is behaving like a hand, opening and closing, but there is no motor there. The other interesting part would be that if I want to make a very small hand, I just need to cut the actuator here and make a very small fingers. It'll still work. Okay, unlike a DC motor will not work, which will not work at a very small scale. So these are called smart actuator based robotic systems. Then we have robots for exoskeletons, so for assisting humans. So these are some of the robots that can assist humans. They can wear these robots. It can help the person climb stairs, carry heavy weight. Autonomous transport, buses, which we already have today. Autonomous transport, okay, buses which operate without a driver, buses and trains also these days. New things like electroactive polymers, again, which can be used to make face of robots. Okay, and it can change the facial expression. Okay, now for example, happy robot, sad robot, it can move the eyes. But essentially, so this material is electroactive polymer, is exactly same as what I showed you just here. And by giving it voltage at different places, you can make it change its shape. So what would happen is the face can have different expressions. So it is made up of this material only. Okay. Then brain-computer interfaces, we can take signals from the brain and then actually actuate a system. Autonomous tracking, driver tracking. These are some examples of robotics applications that we looked at, which have been there and which are already there. Okay. What we'll do is, so today we will stop here. And today was very basic introduction where I tried to talk about where robots came from, and I tried to show you how the robotics technology actually evolved, right from early automation, that is about 10,000 BC. That is very, very long time ago. And from there we had hard automation, that is mechanical automation. Then with the invention of the transistor, we had the invention of the microprocessor. And from the microprocessor, we have microcontroller, and then we had DSP in that order. So what we see is that robotics essentially came about as a part of automation with the invention of the transistor and the microprocessor, where you could have a mechanical system to be reprogrammed to do a particular task. Now in the next class, we'll move on to the next part, that is robots are made up of joints, and joints are actuated by actuators. And we'll look at, after that we'll look at transformations, that is when it is robotic system is moving. One of the bases, the base of the robot is fixed, where we attach the base frame or the world frame, which is not moving. And then whatever is moving is with reference to the base frame now. Okay, that basically we'll have to look at transformations. So today we'll stop in this lecture and we'll continue the next lecture. Thank you.